Or did you go?
Yeah, I'm trying to find
Welcome to the security seminar here at Purdue University. It's my great pleasure to introduce today's speaker, Dr. Ting. Ting received a PhD in computer science from University of Illinois at Urbana-Champaign in 2003, and currently he's a faculty member at North Carolina State University. His research interests include automated trust negotiation, trust management, privacy policy specification and management, and also data privacy. Here's Ting.
Right. So thank you. Thank you very much. It's really a great pleasure to give a talk in the security seminar. And today I'm going to discuss how to define compromised sensor nodes in wireless sensor networks. So this is a joint work with Ting and Peng at our department. So recently there's a huge interest in wireless sensor networks. So in wireless sensor networks, we pretty much deploy low-power, inexpensive sensors in large geographic areas. So the property of wireless sensor network is that after deployed it, those sensors are going to self-configure themselves and configure into a network. So because of this property, it has been envisioned to have a very broad applications. So for example, we can use it for target tracking, battlefield surveillance, and environmental monitoring. So in particular, because once you deploy it, it's going to self-configure into one network, it is very suitable for event tracking in open hazard environments. Okay. But on the other hand, wireless sensor networks have imposed great security challenges. In particular, because sensors are deployed in open systems, they are very vulnerable to physical attacks. Anybody can just access the sensor physically and may try to compromise the sensor. So in the worst case, the attackers may just extract all the key materials. So in this case, the attacker may just completely impersonate that compromised nodes and introduce arbitrary false information into the system. Okay? So in that context, cryptographic techniques may not be helpful because the key has been compromised. If you want authentication, I can do authentication. Okay? I can also encrypt my data as you want. Okay? So how are we going to identify compromised sensors? That is the topic of this talk. Okay? So here's the outline of the talk. So first, I'm going to present a framework for identifying compromised sensors in wireless sensor networks. So our approach is not specific to any applications. Instead, we want to extract the intrinsic relevant properties so that we can run algorithms to identify compromised nodes. Okay. Then we're going to present the design of identification function. We show that this function is optimal in the sense that we're going to identify the largest number of compromised nodes without introducing any false positives. Okay. Later on, we're also going to present some techniques to further increase the number of compromised sensor nodes in the cost of introducing some false positives. I'm going to show some experiment results to show the effectiveness of our approach. And finally, I'm going to conclude this talk and briefly discuss the directions for future work. Okay. So the problem of compromised sensor nodes has been recognized in the literature, and there has been several approaches has been proposed. So basically, those approaches can be divided into two categories. So in the first category, people try to detect and tolerate the false information introduced by compromised sensor nodes. For example, in data aggregation, we may introduce redundant sensor nodes, or we may do some random sampling. So in hoping that if we find some information which is very different than what expected, then I just filter out those information. So hopefully the information I got finally does not deviate too much from the true information. Okay? So in this approach, however, we cannot identify precisely where this false information is introduced. We may not be affected by the false information, but we don't know exactly which nodes are compromised. And in the second category, we call it alert-based approach. So in this kind of approach, the application introduces some specific detection mechanisms so that sensors may observe each other's behavior. Okay? If I observe something weird, then we just send alert to the base station, say, hey, look how this guy is bad, probably bad. Okay? So by looking at those alerts, we may be able to pinpoint exactly which node is compromised. But the problem is that good nodes may issue alerts against bad nodes, but a bad node which is compromised may also issue false alerts to mislead the judgment of the base station. Okay? So when we receive a bunch of alerts, we really don't know which one is valid, which is not. How are we going to reason about it? How can we know which node is compromised, given a bunch of alerts? Some are false ones. Okay. So when we first look at the problem, the first thought in my mind is that, well, wait a minute. You have a bunch of nodes talking to each other, and you have alerts issued against each other. So this is quite similar to like online auction community and eBay. People get service from each other, then issue feedback, evaluate others' service. A lot of work has been done on reputation-based trust management in P2P systems and online auction communities. So can we just apply those techniques directly into a valid sensor networks? Okay. And after further investigation, we found that in sensor network, there are some unique properties that are quite different from the P2P system or online auction communities. So first thing is that in a P2P system, any two nodes can talk to each other. There's no restriction who you can talk to, who you cannot. But in various sensor networks, we have some deployment topology. A node may only interact with others around it. We cannot have interaction between two nodes that are very far away from each other. Okay? So in other words, we have some topology there for detection. Okay? So because of the topology, local majority is a severe problem. Because if I know that this node can only talk to 3 nodes, then I can compromise these 3 nodes. Then I can just badmouth this specific node. Okay? And so that is challenging here. But on the other hand, in P2P systems or online auction communities, every node is really selfish. Okay? I want to get the best from the system, and I don't want to jeopardize my own benefit. Okay? But in sensor networks, it's more or less a distributed system. Okay? All those nodes collaborating with each other try to achieve one common goal. So in that sense, it's maybe possible to achieve a global optimal by sacrificing some specific nodes in the system, in the sensor network. This may not be possible in a P2P system. Okay? If I have to issue alert and sacrifice myself, then probably I'm not going to do that, okay? Because I want to protect my own benefit. Okay? So look at this uniqueness of sensor networks. We observe that they bring both challenges and opportunities to identify compromised nodes. So we want to take advantage of those properties. So next, I'm going to present an application-independent framework for identifying compromised sensor nodes. Okay, so in this framework, we make the following assumptions. The first one is that because we are targeting at alert-based approach, so we assume that there exist some application-specific detection mechanisms. So in other words, we have some way that for one node observe another node's behavior. Okay? So that is provided by the application. And second, we focus on static sensor networks. That means once a sensor is deployed, its position does not change dramatically. So one implication of this assumption is that the observation relationship between different sensors does not change once you deploy the sensor network. Okay? And then we assume there exists some basic security primitives to protect message confidentiality integrity. So even when a sensor issues one alert to the base station, we know that it is not compromised, and we know who issued this alert. Okay? So finally, we assume the base station is trusted, and it also has sufficient computation and communication powers compared to sensors. So in our approach, we adopt a centralized approach, which means that for sensors, they just need to observe each other's behavior. And if there's something wrong, they just need to issue alert to the base station. All the reasoning is done by the base station, not by the sensor. Okay. So here's the basic components of the proposed framework. So first we have the observability graph. So this pretty much represents the relationship between the sensor nodes who can observe whose activity. Okay? So V is a set of nodes whose integrity we care about. Okay? We may not care every node's integrity. We may just care a subset of them. Okay? And one edge from S1 to S2, if only if S1 can observe the behavior of S2. And S1 may issue an alert against S2 sometimes. Okay? And the second component is alert. So we model alert as a tuple which composed of 3 values. First one is the time the alert is issued. And then who is the issuer of the alert, S1. And who is the target of the alert, which is S2. So which means that at time t, S1 issue an alert against S2. So we may further enrich this alert to include more information. For example, how confident S1 is about the alert. But for simplicity, we just have these 3 values here. Okay? And note that a sensor may not be perfect. Even though a sensor is not compromised, maybe because the accuracy of the sensor, it may not always report the 100% accurate information. Okay? So here we use a sensor behavior model to model the sensing quality of a sensor node. So similarly, we depend on detection mechanisms, and the detection mechanism may not be perfect. Okay? So it may also make some mistake from time to time, even though nothing is wrong with the system. So we're using observer model to model the possibility that detection mechanism giving you some wrong answer. Okay? So the next parameter is called security estimation. Basically, this is the upper bound of the compromised nodes in the system. So obviously, if all the nodes can be compromised, then there's no way you can detect which node is compromised. So we assume that somehow the application can get an upper bound of the number of compromised nodes. Okay. Finally, we have one component called application identification function F. So given all the above information, this function is going to give me a list of sensors which we believe is compromised. Okay. So let's look at an example that how we can, using the framework, to model some sensor applications. Okay. So one application is sensor network localization. Okay. In many applications, it requires that we know the location of a sensor. Okay. For example, if you're talking about event tracking, I need to know that where the event happened. So I need to know not only that there's some event happened, I also need to know the location of the sensor node. Okay. So it's very expensive to equip a localization device on every sensor node. Okay. So one basic approach is that we have some beacon nodes in the network. Those are those sensor nodes who knows their own locations. Okay. Maybe they have some GPS device equipped with them. And for the other sensors, they're going to talk to the beacon nodes nearby to get some location references. Okay? So from those location references, I can estimate or derive my own location. Okay? But the problem is that if one beacon node got compromised, the beacon node may just claim arbitrary location. Okay? Then cause other sensor nodes to derive their location forcefully. So in 2005, Liu et al. Proposed one detection mechanism for compromised beacon nodes. So the basic idea is that they try to let beacon nodes nearby to probe each other. Okay? I know my own location, but I pretend that I don't know my location. I talk to some other beacon node. Then I compare the measured distance between the two sensor nodes and the derived distance between them. If they are very different from each other, then I know that the other beacon node is giving me wrong location references. So I may issue alert to the base station. Okay? So clearly, if a beacon node is compromised, he may also just say that the other beacon node is compromised and issue alert. So how are we going to model this sensor network localization service by using our framework? Okay? So here I show one deployment of a sensor network, and the rectangle nodes represent beacon nodes. They know their own location. And the circles represent those common sensor nodes. Okay? Yes?
This may be a very silly question, but are the beacon nodes fixed?
You mean fixed mean the location is fixed? Yeah, usually we assume it's a static network. So once you deploy it, it just stay there. Okay? No, they don't move. The static network. Okay? So in this case, we see that, for example, S2 may get location references from B1, B2, B4, and B3. Okay? So here we cared about the integrity of beacon nodes. So in our observability graph, we may only have beacon nodes here. So we have edges between B3 and B4 means that they may probe each other. Okay? B3 may try to probe B4 to see whether they're given the right location. Okay? Then how about the sensor behavior model and observer model? So those are all related to the accuracy of the distance measurement. If the distance measurement is not accurate, then you may have a not accurate observer model here. Okay, those are application specific. And the security estimation can also be determined by the application. Okay. So now suppose we're talking about localization. And now the base station received a bunch of alerts. So how can I know which beacon node is really compromised from those alerts? Okay. So because beacon nodes are not perfect, if you only receive one alert, it may not mean much, right? Maybe it's just an innocent mistake. But if during one period of time, I received excessive amount of alerts from node S1 to node S2, then I know that probably there's something wrong. Okay, and so we call such edge abnormal edge. That means that during this period of time, something wrong between this pair. From this abnormal edge, I can now tell which node is bad. Maybe S1 is bad. S1 just issues a lot of alerts against others. Maybe S2 is really bad. S2 gives a lot of false location reference. Okay, but I can know for sure that at least one of them is bad. Otherwise, there should not be so many alerts between them. Okay, so we also call it a switch pair. Means that given this pair, I know for sure at least one of them is bad, is compromised. Okay, so obviously, this is one situation. I know there must be one of them bad. So in another situation, suppose S1 and S2 are observing the behavior of the same node S3. But S1 thinks S3 is good, but S2 thinks S3 is bad. Then I know that one of S1 and S2 must be bad. Otherwise, this should give me the same consistent evaluation of S3. Okay? So we can identify suspicious pairs by based on these two conditions. Either you have issued a lot of alerts between these two pairs, or you have different assessment of the same node. Okay. So by collect all those suspicious pairs, I can construct an inferred graph, which is basically composed of all the suspicious pairs. Yes?
So is it possible for a bad node to report correct information to one node, but incorrect information to another?
That's possible. That's possible. So let's look at it.
So is it possible that S1 is issuing that abnormal edge because it can see more information compared to what S2 can see?
So that should be reflected in your observability graph. So if you can observe another node's behavior, then there should be edge between S1 and the other node.
But that model, it models it at 1 or 0, observe or not observe. Mm-hmm. But maybe you can observe to 90%. Like if you are very close to a sensor, you can see it better, or you can see more of the traffic.
Right.
But if you are farther, you can see much traffic. So.
Yes. So it's possible, but in that case, you have to enhance your alert. For example, not only say, I think S2 is bad, I also need to give some confidence. Because, for example, S2 is very close to me, then I'm very confident. If it's far away, then I'm not that confident. But so far in the model, we just assume it's 1 or 0. Okay. So just give example here. Suppose this is abnormal edges I've obtained in the observability graph. Okay. So the yellow edge means that it's abnormal edge, means one node issues a lot of alerts against another one. And the white edge arrow means that everything is okay, it's normal. Okay? So from this observability graph, we can derive this inferred graph. Okay? So know that 2 and 3, there's edge, obviously because 3 has issued a lot of alerts against 2, node 2. Okay? And 2 and 5, the same reason. Note that we also have one edge between 2 and 4. The reason is because 2 thinks 5 is bad, but 4 thinks 5 is good. But they are observing the same node, so there must be something wrong between these two nodes. Okay? And I want to point out that the suspicious pair relationship does not propagate. Okay? So if you have one normal edge, for example, from 6 to 9, you cannot say for sure that either they are both good or they are both bad. Okay? Because maybe this 6 is compromised, but 6 just don't care to say something bad about node 9 here. Okay. So and another example, for example, from 3 to 2, there's a suspicious pair, and 2 to 1, everything is okay. But we cannot say that 3 and 1 are suspicious pairs.
So does it mean among 2 and 4, you believe that one guy is bad?
Between 2 and 4 or 1 and 4?
2 and 4.
I believe one of them must be
But
bad.
it could be they're both good, just 5 is showing different aspect to one of them. So one of them thinks 5 is bad, the other thinks 5 is good.
So here we assume when you observe something, you observe the same behavior, the same activity. For example, if you say that packet dropping, then whenever you send something, I know you receive something, you should send out the packet routing. So they can observe the same behavior. Okay.
But how can you observe the same behavior if they are in different locations?
Who are in different locations?
The nodes. You know.
And
Like if 2 and 4 are in different locations.
But they are all close to 5, so they can all observe the behavior of 5. Because so if there's edge between say 8 and 9, that means 8 can observe the behavior of 9. Otherwise, there should be no edge between 4 and 5 at all. Okay.
Just
Yes?
to make sure, if a good node observes something bad, it will always report it.
Yes.
Okay.
Yeah. So here we say a node is compromised, but maybe the node is not compromised. The node may just be defect and behave very weirdly. So we just also consider that the integrity of that node has been compromised. Okay? It may not be because of the tiger. Okay. So given the inferred graph, how can I know which one is compromised? Okay. So obviously you want to, we have the concept of value assignment. So this is basically one possible way that nodes are compromised, which is going to result in the inferred graph. Okay. So formally, it's really a partition of all the nodes in the graph. Some are good, some are bad. Okay. And there are two requirements. The first requirement is that a suspicious pair, S1, S2, should not belong to n good. That means if there's a suspicious pair, they cannot be both good. Okay. Another one is that the bad node, the number of bad nodes should not be bigger than your security estimation, because K is the upper bound of the number of compromised nodes. Okay? So if we find such a partition, satisfy these two conditions, we say it is a valid assignment. Okay? So in the previous example, maybe we can say that suppose K equals to 3. Then we may say that 2, 4, 5 are compromised, but 1, 3, 7, 8 are not. Okay? But it's also possible I just say that 2, 4, and 4, 5, and 3 are compromised. Okay? So generally, given an inferred graph, there are many possible assignments you may have. Okay? But then how can be sure that one node is compromised? The observation here is that if every assignment tells you that this node is compromised, then this node must be compromised. Because no matter how you assign a compromised node, this node is always included as compromised. Okay? So we call such node form the compromised core given the inferred graph. Okay? Basically means that these nodes in the compromised core must be compromised, no matter how you're going to assign those nodes. Okay? So this compromised node is really the intersection of all the bad nodes in every possible assignment. So given identification function, we say it is optimal if it can identify the largest number of compromised nodes without introducing any false positives. Then we say it's optimal. Clearly, it's the same as compute the compromised core, because this core contains every compromised nodes that every assignment believe they are bad.
What if the intersection is null?
So in that case, you cannot say for sure.
But still, you have that graph that says that there is a compromised node.
Yeah. So if the compromised core is empty, that means that we cannot say for sure which node is compromised. But it doesn't mean that we cannot do anything with it. We're going to discuss that later. Okay. So in our discussion, we assume a very general collusion model. That means we don't assume any specific collusion between sensor nodes. So the sensor nodes may coordinate with each other. They may not issue alerts against each other, but they may also issue alerts against each other. Okay? So basically, they can do whatever thing they want. Okay? And so in this case, the inferred graph may be of any topology. But still, we have the observation here that given the suspicious pair, at least one is compromised. So no matter what kind of collusion model they follow, this is always true. Okay? So we want to start from this point to reason which nodes are compromised.
Question?
Yes?
So when you say general model, you don't mean the most powerful adversary model.
Mm-hmm.
Because I can think that a more powerful adversary model would assume perfect collusion.
Mm-hmm. Yes. So in our paper, we actually assumed a very, as you mentioned, a strong collusion model. Basically, we assume that a node does not, two compromised nodes do not issue alerts against each other. And if they observe the behavior of the same node, they always issue alerts consistently. Okay? And now the question is that whether, even though they're colluding, whether the base station knows that or not. If the base station does not know this knowledge, then we have to assume that there's no such collusion at all. Actually, I lost some information. I cannot do better than assuming that you can do anything you want. But on the other hand, if the base station knows they always follow this strong collusion model, then I can take advantage of it. Okay? So by assume a general model, I assume that the base station has the least amount of information to inform compromised nodes. This is the worst case, actually. Because
Yeah, I can take the further discussion offline.
okay. All right. So here, let's see that suppose we have a inferred graph here. Okay. And one observation here is that, in fact, the valid assignment in the bad node of the valid assignment actually forms a vertex covering of your inferred graph, right? Because for each edge, you must assign at least one of them as bad one, right? So in that case, at least one node is going to cover one edge here. So your valid assignment, the bad nodes in the valid assignment actually is the vertex covering of this inferred graph. Then the minimum vertex covering actually gives you the lower bound of the number of nodes that are compromised in the system. All right? Okay. So now let's look at the following scenario. Suppose now I want to know whether node S is compromised. Okay. Suppose node S is not compromised, and let NS be the neighbor of S in the graph. Then I can say for sure that all its neighbors must be compromised, right? Because S is not compromised, and I have an edge between S and its neighbor, then the other one must be compromised. Remember that in each edge, one of them must be compromised. Okay? So I know that at least here, all the neighbors are compromised. I remove S and its neighbors and let the resulting graph be GS. Then how many compromised nodes in the resulting graph? At least you have some number of minimum vertex covering of GS to cover the remaining graph. Okay? So if I assume S is not compromised, I know that there should be at least NS plus the minimum vertex covering of GS number of nodes are compromised. Right? So if this number is bigger than K, then I found a contradiction because k is the upper bound of number of compromised nodes. So if this is bigger than k, that means that my original assumption is not correct. So node S must be compromised in this case. Okay. And we show that this is not only a sufficient condition to say that node S is compromised. Actually, this is also a necessary condition. So if you can identify all such node S, then you can actually get the complete compromised core you want to compute, and without introducing any false positives. Okay. So in general, our algorithm is composed of the following steps. For every node S, I'm just going to get rid of S itself and all its neighbors in S. Then I'm going to compute the V, which is the size of the mean vertex covering of the remaining graph, GS. Okay? If V plus the number of neighbors of S larger than K, then I know that S is compromised. Okay? But as you all know, that minimum vertex covering is NP-complete problem, so you don't want to compute it. So in our algorithm, we're actually using some lower bound to approximate the minimum vertex covering. What we use is a maximum matching as a lower bound approximation.
Can
Yes.
you do one slide? The if statement at the end, you are computing some metric and comparing it to K.
Mm-hmm.
Isn't it very analogous to reputation-based techniques?
I'm sorry?
Isn't it very similar to reputation-based techniques?
Very similar to reputation-based
Yes.
techniques.
Where the reputation here is someone telling on you that you are misbehaving or no.
Mm-hmm.
So it is very related to reputation-based. Right?
Well, yeah, here we're using the topology information to get a closer bound of the number of compromised nodes, because I know that NS is my neighbor. Okay? But in a P2P system, for example, you don't know that. Right? You don't know which, because anybody can be your neighbor in the P2P system. And also, because in sensor network, several nodes can observe the behavior of the same node. Okay? But in P2P, usually, one transaction, there's only two parties involved. Okay, so that's the difference between the typical P2P system and sensor network system. In fact, in later experiments, we're going to compare our approach with a well-known P2P reputation-based trust function to see what's the difference between them in terms of performance. Okay. Okay, so instead of really compute the minimum vertex covering of a graph, we actually use the maximum matching as a lower bound approximation. Okay. Note that here we don't want upper bound approximation. We only want a lower bound approximation, so that we're not going to introduce any false positive. Okay. But maybe we're not going to identify all the nodes in the compromised core. But I'm pretty sure that I cannot introduce false decisions here. So now come to the question previously asked. Suppose after I remove all those compromised nodes, there may still be suspicious pair remained in my graph, right? I mean, so what happens? What should we do with those nodes? Okay, with those nodes, we cannot make a reason for sure that which node is compromised. But again, because this is a sensor network, I want to achieve optimal security of the network. I may just sacrifice some nodes. Okay, I may have a trade-off between the detection rate and false positive. So one easy way is that I just identify the maximum matching of the resulting remaining graph all as compromised. Okay? And so given one pair, I know one of them must be compromised. So if I identify both of them as a compromised, I introduce at most 50% false positive rate. Okay? That's a bound I can guarantee. Okay? Actually, I can do better. Suppose I don't identify maximum matching. Identify all those triangles, disjoint triangles in the remaining graph. Then I can lower down the false positive rate to 1/3. Okay. So in summary, our approach is composed of two phases. In the first phase, I'm going to approximate the compromised core. in this phase, I'm not going to introduce any false positives. Okay. Then in the second phase, I'm going to use maximum matching to further eliminate compromised core in the resulting remaining graph. Okay. Okay. To verify our approach, we set up some simulation here. So in the simulation, assume that sensor nodes are randomly deployed in a 100 meter times 100 meter area, and they are sensing the temperature and report the temperature back to the base station. And we also assume that there are 10 to 15% nodes are compromised. Okay, and we actually assume a strong collusion model. That means those sensors always collude with each other. They're totally coordinated. So I don't issue alerts against my another compromised node. And if we observe the same node, we're going to issue consistent alerts. Okay. In other words, there's no edges between compromised nodes. Okay. But we don't assume the base station knows that. The base station may still just assume the compromised nodes may behave whatever way they want. Okay. So it cannot take advantage of this information. Okay. So what do we care here? We care about two things. First, detection rate. That means how many compromised nodes I can identify. Okay. Another one is false positive rate. That means how many wrong decisions I made after I identify compromised nodes. There are several parameters we want to determine their impact on the performance. So the first one is deployment density. Intuitively, if you only have several beacon nodes, several nodes in your network, you cannot do much. Okay? But if you have more nodes in the system, then the behavior of one node may be observed by a lot of other nodes. Okay? So in that case, we may choose better. We want to observe what is the impact of deployment density to our algorithm. Okay? And the other one is accuracy of security estimation. Maybe you just make a wrong decision, which you are very conservative. You assume that there's so many nodes may be compromised, but actually there's only a very small number of nodes actually compromised. Okay? So we're going to see that what is the impact of accuracy of your security estimation on our algorithm's performance. Okay? So we compare the following algorithms. The first one is called general only. That means this algorithm is only composed of the first phase. I compute the compromised core, I stop there. Okay? So in this case, I'm not going to introduce any false positive, but I may miss a lot of compromised nodes. Okay? And in the second is called general plus MN. That means I have a two-phase algorithm. I compute the compromised core, then I'm going to use maximum matching to further eliminate compromised nodes. Okay? I may identify more, but I may also introduce false positives. And we also have implemented another algorithm called eigenrep. This is a well-known reputation-based transfer function for P2P systems. So this algorithm is very similar to a page ranking algorithm when you try to fetch a web page by a search engine. Okay? So by running this algorithm, when the algorithm stops, it's going to give a trust value for every node in the system. What we do is that we just identify the k nodes with the lowest trust value as compromised nodes. Okay? So we're going to see that by taking advantage of the special property of sensor networks, can we do better than treating it as a general decentralized P2P system. Okay. So this shows the deployment density's impact on the performance. Okay. On the left, we have detection rate, and on the right, we have the false positive rate. Okay. And so we vary the number of nodes in the system from 50 to 250. Okay. So the first observation here is that the eigenrep is not going to achieve the same detection rate as general plus MN. Okay. So that means if we have two-phase algorithms, I'm going to do better than the eigenrep algorithm. Okay? But by only compute the compromised core, general plus general only algorithm, then the detection rate may not be that good. But another observation is that the more sensors you have in the system, then intuitively you're going to achieve better detection rate because now you have more information to reason about. Okay. Now let's have a look at the detection rate, the false positive rate. Okay. For the general only, obviously the false positive rate is 0 because we never make a wrong decision. We just compute the compromised code. Okay. And for the general plus MM, the two-phase algorithm, it's actually the detection rate, the false positive rate is always lower than eigenrep. Okay? So basically compare general plus MM and eigenrep, we see that we can have better detection rate and a lower false positive rate. Okay. Okay. So another factor, which is accuracy of your estimation. Okay. We assume that in this experiment, we assume that there are always 20 nodes compromised in your system. But I changed my security estimation from 20 to 40. I mean, sometimes maybe I have a very tight estimation, but maybe my estimation is very loose. Okay. So we see that the first observation here that for general plus MM, we actually achieve pretty high detection rate, no matter whether your detection, whether the security estimation is tight or not. Okay. But for the general only, that means only run the first phase, then when the security estimation is not good, then we may have very bad detection rate. In the worst case, we may not detect anything by using this loose estimation. Okay? So this also shows that what the maximum matching can give us. That means when we have 40, almost all those compromised nodes are detected by using the maximum matching using the second phase. Okay. And again, we observe that eigenrep cannot achieve high detection rate as high as the general plus MM algorithm. But one interesting observation here is that it seems as you increase the security estimation, the detection rate also actually increased. Okay. The reason is because now I include more and more nodes in my reported results in eigenrep. So by chance, I'm going to include more compromised nodes. Okay. But that is going to significantly increase the false positive you're going to introduce. So that's why we see that this is the detection rate of the eigenrep, the false positive rate of eigenrep is always higher than the general plus MM algorithm. And we see that the general plus MM algorithm's false positive rate is always bounded by 0.5. Okay, that's consistent with what we discussed before. Okay. So in conclusion, because sensor networks are subject to physical attacks, so compromised nodes may impose a severe threat to the security of sensor networks. So in this work, we propose a general framework to identify compromised nodes. We try to take advantage and model the uniqueness of sensor networks. Then we can propose optimal identification algorithm in the sense that we identify the largest number of compromised nodes without introducing any false positive rates, any false positives. And we also discuss some techniques to further eliminate compromised nodes. Okay? And we use some experiments to evaluate our approach. Okay. Okay. So for future work, so far we are taking a centralized approach. That means everybody send an alert back to the base station. Okay? But this may cause high communication cost. But sometimes it may not, because sometimes the alert may just be inferred by looking at the information sent back by the sensors. They don't need to be explicitly sent to the base station. Okay? So another possible way is to use a decentralized approach. Basically, sensors looking around itself and reason which node are compromised. Okay? So this may give you a less communication cost. But because you don't have a global view of the network, your decision may not be that accurate. Okay? And again, we don't want to use a generalized, decentralized approach for P2P systems. We still want to accommodate the uniqueness of sensor networks. Okay? And another direction is about sensor network reconfiguration. After you identify the compromised nodes, how are you going to deal with them? One natural choice is that I'm going to get rid of those nodes from my system. For example, I revoke all those keys of compromised nodes. But once you remove those compromised nodes, the functionality of the network may also be jeopardized. You want to cover the whole area, but after you remove those compromised nodes, this area is not covered anymore. Okay? So how I can efficiently and cost-effectively maintain the functionality and security of sensor networks? So this is actually a challenging issue because you not only consider one operation, you want to consider the functionality of the network during its whole lifetime. Okay? So this is so when you make a decision, you want to think about what might happen in the future. So what is the best approach I can take to affect the future? Okay. Okay. So that concludes my talk. Thank you very much. Any questions? Yes, Mike.
So I just want to make a comment that the maximum matching approximation is in fact not an approximation in some situations. It's an exact solution. It's precisely when, and you can actually force that to happen. It's an exact solution to the, that is, the problem is no longer NP complete if the graph has no odd length cycles. And you're in control, and you could perhaps make sure there are no odd length cycles.
I see.
By carefully planning the who checks who. So, for example, if you in one round you have the reds and the blues, and you can only check one of a different color, there can be no odd cycle.
Right, right.
And then you have an exact solution. So I think one of the reasons it's doing so well is it's not an approximation at all. It's actually finding, in many situations, I don't know how many times this has happened.
Right. Right. Actually, I tried both. Actually, I tried both mass matching and vertex covering, but the result is always pretty much always the same.
Well, maximum matching is the best way to solve the covering problem.
Yeah, this is best approximation.
And it's an exact algorithm. So I'm not surprised that MM, I guess, is doing so well.
Okay. Okay. But if you only using MM, sometimes because the security estimation is not good, then you may just introduce false positives.
It deserves to do good. Is what I'm saying.
Okay, thank you. Other questions? Yes.
Also, I had a common question. When you mentioned in the beginning that your graph consists only of the nodes of those integrities of concern, and I assume that implies there could be other nodes that are trusted. And I thought that if there are some nodes that are trusted at all times, and they can also observe other nodes, then you can, if you include their information in the graph, the algorithm is going to be quite different and maybe more reliable.
Yes.
Because you get reliable input.
Yeah. That's a really important comment. So far we don't assume any. So whether we trust this node more than that one. So in practice, maybe you can assume that if a sensor is close to the base station, that base station can observe the behavior of that sensor. Then maybe I can have more trust on that sensor. So I should trust the information from that sensor more. So we haven't considered that scenario yet, but that's really a good comment. Yes?
So you mentioned in the beginning that the sensor networks are different in a general P2P network. You just by using the standard repetition system may not work that well. But from the talk, it's not clear to me where you leverage the difference in sensor network to get better result. I think I want to ask. So can you use this approach backwards to the
P2P system?
Yeah.
So I think that the major thing is that in the observability graph, so that defines who you can really interact in the system. In P2P system or in online auction, you cannot define such the observability graph because you cannot specify that you can only talk to Alice and Bob, but you cannot Carol, because anybody can talk to anybody in P2P or online auction. But here we have this restriction. That's why that when I think that this guy is bad, when I assume S is compromised, is not compromised, then I know that all its neighbors must be compromised. But in P2P, you probably cannot say that.
And also in P2P, you probably cannot get the same observation.
Yeah, you cannot. It's hard. In P2P, usually one transaction involves two parties.
Okay.
And also that in P2P, you cannot just say, because this is a bad transaction, then I'm going to lower the rating of both parties. Then some people are going to complain. But sensors, they're not going to complain. Okay. Other questions? Yes?
Have you experimented with without doing the inferencing part? Because I think for some applications the inferencing makes sense. But for some applications, maybe you cannot do the inference, even though two guys they have an inconsistent view about the node. It doesn't mean one of them is bad. Maybe both of them are good. So somehow they cannot. They're observing different behavior. So have you tried it without doing the inferencing? And in that case, how well is the detection rate?
We didn't try that, but I think that in some applications, it's really not the case that everybody can observe the same behavior.
Right. And so yeah, for those this is for those kind of applications. I'm just curious.
Yeah, I think that's interesting to try it. We haven't tried that. And actually, another interesting thing is that here we only say that if your security estimation is too conservative. So what happens if actually there are 30 compromised, but your security estimation is only 20? That means in that case, what happens? We haven't tried that because that really cannot give any guarantee about the optimality of the algorithm.
Okay, so let's thank the speaker.